Day 9 and another very tricky puzzle. Today was the first day that we ended up using recursion. So let's go ahead and check out the puzzle. Let's start with part 1. Today's input data is straightforward. Each line starts with a move command, up, down, left, or right, followed by a number, how many steps to take in that direction. We're asked to imagine a two-dimensional plane, an x-axis and a y-axis, and a two-parted little snake that moves along that plane. The puzzle mentions ropes and knots, but this is how I saw it. The first part of the snake is called the head, and the second part the tail. The head takes the move command, for example, right 4, and moves right one step at a time. The tail then needs to follow the head according to a set of rules. If the tail is not touching the head in any direction, including diagonal, it has to take the closest path to keep up. Check out the puzzle description on the website for a more detailed explanation. The link is in the description. Our task for part 1 is to figure out how many different positions on the plane the tail visits at least once. Now let's look at how I solved it. I go through the input line by line and split each line on space to get the command and the steps. To keep track of the head and tail position at all times, I create two variables. Each variable is a string with two numbers separated by a hash. The number on the left is the x position and the number on the right is the y position. Both the head and tail start at position 0, 0. I then split those strings on each line to have easy access to the x and y position of the head and tail. Next, I create a loop that will run for the amount of steps to be taken. I make sure my variables are numbers, and then depending on the command, I move the head by increasing or decreasing the x or y position. Once the head is moved, I need to figure out where the tail should move, or if it should move at all. The tail's x position should move if the difference between the head x and tail x is larger than 1, or if the x difference is 1 and the y difference is larger than 1. If it should move, I increase or decrease the tail's x position depending on which side the head is on. I can then use the same algorithm to figure out if and how the tail should move in the y direction. Since I can't change the tail's position while calculating, I save the tail's movement in different variables and only update the tail at the end. Once I have the new head and tail position, I update my position variables with a new x and y string. To keep track of the positions the tail has visited, I push every position into an array. Lastly, I create a set from the tail positions array and check the size of that to get how many unique positions the tail has been in. I run the script against the example data, but I get the wrong answer. Luckily, I quickly realized my mistake, comparing x positions where I should be comparing y positions. Fixing that gives me the right result. I run it again against my own input and go to submit. Oh yes, seeing that right answer screen is always such a pleasure. In part 2, we are thrown a bit of a curveball. Instead of just a head and a tail moving around the plane, we now have a snake that is 10 points long, 1 head and 9 tails. The head will move just like before, but each tail will follow the one in front of it. The first tail follows the head, the second tail follows tail 1, and so on. This is a case where recursion comes in handy. Our task is the same as in part 1. How many positions does the last tail visit at least once? I start by creating our snake, an array with 10 x and y positions. I'm going to be able to reuse a lot of the logic from part 1, but I need to move it to a separate function called moveSnake. The moveSnake function will take 4 arguments: the first position to move, the second position to follow, the current index in the snake array, and the direction to move in. In moveSnake, I go through the same logic as in part 1. The magic happens at the bottom. If we're at index 8, so the second last point in the snake, we return. Otherwise, we call the same function again, but passing in the next set of points together with an increased index in the arguments. This will run through the whole snake, making sure that each point gets updated based on the previous point's position. Once we end the recursion and return, we're also saving the position of the last tail in the snake to an array, just like before. Lastly, like in part 1, we create a set and check the size and go to submit. It's correct, and a huge relief floods my body. It's now around 7:30 a.m. and I can finally go get some coffee. If you enjoyed this video, please let me know in the comments below. Hit the like button, maybe even subscribe to the channel. That would make me really happy. Have a great day. Ciao.